My co-author on this presentation is a gentleman by the name of Keisuke Kuroda. And as you can see, Keisuke has held various positions within Idemitsu and is our technical advisor from Japan. So here are the key points we want to make in this presentation. Why do we need a polymer quench? What should we do to maintain a polymer quench? And is it possible to reduce the amount of maintenance for a polymer quench? Our table of contents is, what is a polymer quench? We'll talk about what constitutes that. How does a polymer quench deteriorate? How do you maintain a polymer quench? And lastly, how do you actually select a polymer quench? Is much faster than oil, but it's slower than water. The benefits are it gives you high quench hardness, it's not hazardous. The drawbacks are it can grow bacteria, it can rust, and if you're not careful, you can have distortion and cracking. So here are various types of polymers that were used in the past and looked at. Polyvinyl alcohol, polyvinyl pyrrolidine, sodium polyacrylate, polyethylene glycol, and what's most commonly used today is polyethylene glycol. That's because the proper polyethylene glycol, or PAG, is very stable with thermal degradation, and it doesn't shear as easily as a lot of these other polymers did. Chemically, this is what a polyethylene glycol looks like, but a polymer is more, or a polymer quench is more than just a polyethylene glycol. There's fatty acid salts, amine salts, which are rust inhibitors, biocides. We have surfactants in there, defoamers. Surfactant is something that will allow, it's really like a detergent, and it will allow the water-based polymer to coat a piece of metal evenly and uniformly. Now, a polymer exhibits what's known as inverse solubility. And you can see on the left that the polymer is very clear. On the right, when it's heated up to 70 degrees C, which is roughly between 150 and 160 Fahrenheit, it turns cloudy. That means the polymer has come out of solution. And then when it returns back to room temperature, the solution becomes clear again. So what that means is the polymer, when it comes out of solution, you can see here, it coats the part and controls the cooling. It creates a long vapor phase, and then into your boiling phase, and then into the convection phase. Where if it were just water, it would have a short vapor phase. And you notice that this portion here of the boiling phase is the slope of that line is very steep and it's very rapid. And then the PAG, the polyethylene glycol, lessens that slope and it controls the cooling better. So the role of a polymer here, you can see, is we have different, water here, and then these are different concentrations. The higher the concentration, the further to the right the slope moves, or this line moves, and the slower the quench speed actually is. And you can see it extends the vapor blanket stage and increases the convection stage starting temperature. And it reduces the cooling speed at the boiling temperature. Now this graph here shows the maximum cooling rate. So just plain water is somewhere around 1,500 degrees per second. You can see that that's going to be quite fast compared to a 10, 20, and 30% solution of polymer. But as I said, the higher the concentration, the slower the cooling speed, and the less likely you are to have distortion and cracking. So what are the characteristics of a polymer quench? Well, it will be non-flammable. The usage cost is going to be less because you'll be able to dilute your solution with water. And as I said, the cooling rate is controlled by concentration. But it's important to remember that if the concentration changes, cooling performance is also changed. Once rust or decomposition appears, and we'll talk about what is decomposition later in this talk, a dump and recharge of the system is needed. And if a polymer quench is not properly maintained, there will be all types of problems associated with the maintenance. So, again, we can't stress enough that the concentration continually changes due to water evaporation. Daily maintenance is important. We'll talk about what that is. And if the maintenance is different than a quench oil. So how does a polymer quench deteriorate? Well, it breaks down through use. Breaks down through pyrolysis, which is thermal degrading. Breaks down by mechanical shearing. Since it coats the parts, it's dragged out. If it's left untreated, it grows bacteria, which results in acidity or foul odors. It's important to note that bacteria will double in size and in concentration every 24 hours. It's also important to keep oil out, from hydraulic systems or any other types of lubricant type in there, because that causes an unstable cooling performance. It's shorter than the original. Your nucleate boiling phase here, this slope becomes steeper than this, and as you move a cooling curve to the left, it becomes faster. So the performance of the product changes. What other types of contaminants are in there? Well, there's possibility for contaminating oil, which would be from hydraulic oil, so like I said, other lubricants, sludge. That would be where the hydraulic oil or contaminating oil starts to emulsify with your polymer. You can have bacteria, mold, and heat scale is always present. And these can all be taken care of and treated. Heat scale can be filtered. Mold, once that's in there, the system really should be dumped. Bacteria, you can use a biocide. Contaminating oil can be skimmed off and then slowly. So what does forming that oil and water emulsion do to your cooling speed? Instead of moving it to the left and making it quicker, it moves it to the right and makes it slower. Now, if the cooling speed is slower, your microstructure and your metallurgy may be affected. Now, when it comes to bacteria, we're not trying to prevent all bacteria. We don't live in a sterile environment. There's bacteria in the food we eat, the water we drink, and the air we breathe. And that's called aerobic bacteria. We don't necessarily smell it. But what we want to prevent is anaerobic bacteria. And that means without oxygen. And if there's a layer of oil on top of your polymer bath, oxygen can't get in. That creates a very foul-smelling situation. Just think of a teenager's gym locker after sweating all semester long, and they bring those dirty, stinky gym clothes home after not washing them all semester long. How bad that stinks. That's what anaerobic bacteria is. When you turn that sump on a Monday morning, you can clear out your whole plant for several hours. So the contaminants in a some create anaerobic and aerobic bacteria. As I said before, the aerobic bacteria doesn't smell, but it creates sugars and proteins and organic acids that create feeder sources for yeast and mold and more bacteria. Anaerobic bacteria releases sulfates, they produce residues, they create the foul odors, and the sulfates react with iron and copper to create iron sulfides and copper sulfides, which again can affect the metallurgy of your material, and it will affect the tooling, which is made out of copper. Here's what's recommended to properly maintain a polymer quench. Concentration on site every single day. Should be done at least once a shift, at the start of every shift. pH. If you don't have a pH meter, something like litmus paper, and it's very inexpensive, can be used. Cooling rates, viscosity, refractive index, bacteria growth, rust preventative testing, cooling curves, those should all be done by your supplier. It takes a lot of technical ability to run these tests, and also, to run the test isn't expensive, but the equipment is very expensive. And there's no sense in you investing in it when your supplier already has it. What's required for CQI-9? Because I know some of you are automotive suppliers. Well, the analysis according to CQI-9 is dependent on the age of the sump. If you're dumping more frequently than every 4 months, no analysis except daily concentrations needed. However, if your dump cycle is longer than 4 months, you're producing automotive parts that are CQI-9 registered, you have to have cooling curves at a minimum of every 4 months, and the maximum quench speed must be reported. You can't get the maximum quench speed without a cooling curve. So again, if you're more than 4 months old for your sump, send in a sample to your supplier and let them run it. So how do you take a concentration sump side? You use a handheld refractometer, and the refraction, which means bending of the light, will depend upon the concentration. A low concentration or a high concentration will give you a higher number, low concentration gives you a low number. You take that number over to a chart, and the chart varies for every polymer. And you take your bricks percent, draw a straight line over to your curve that you have there, and then look down, and you can determine your concentration. Now, what does the cooling rate do? Well, as we talked about the cooling rate, you move that chart to the left. You move that cooling curve to the left as you used it. And you can see here that you go on a fresh solution from about 325 degrees per second to about 500 degrees per second after quench. What is happening there is your polymer is being thermally degraded through the heat generated in the heat treat process, and it's becoming mechanically sheared by going through the pump that recirculates the polymer quench. We talked about bacteria and pH. Well, this slide shows that you want to keep your pH between 8.5 and 10.5, because below that you can have rust and growth of bacteria. Above it, operators that are very sensitive will start to have skin irritation. And the higher the pH goes, the more people will have irritation to the polymer quench. So now if you have pH issue, what do you do? Well, if you're between 9 and 10.5, you're fine. And you'll have small amounts of bacteria. Again, we're not trying to create a sterile environment. But as you start to get higher and higher in bacteria, that's when you may need a biocide, or you need to consider dumping and recharging. So how do we measure? Well, we have these little dip slides in the lab that we put into an incubator, and this is what we mean when we say 10 to the third, 10 to the fifth, or 10 to the seventh. Same thing with yeast and mold. Yeast and mold, anytime you get mold into your system, something's wrong. And unlike bacteria, you can physically see the mold. Mold can also exist outside of the solution. So even if you put a fungicide into the solution, the mold will continually to release its spores into the solution and continue to contaminate your solution. So you need to make sure that if you have mold, you do a thorough job of cleaning everything, the covers to your tank, all of the areas in the tank, to get rid of the mold. Otherwise, it will continually come back. Cast iron chip test is how corrosion is measured. You weigh out a prescribed amount of dry machined cast iron chips and put it on a filter paper. You cover it with polymer and allow it to sit for 24 hours. And then you evaluate the rust on a scale of 1 to 5. And you can see scale of 1 is no rust, 5 is gross amount of rust. The lower the number, the better. So maintenance of a quench, or a polymer quench. Pre-washing is important. You want to make sure that whatever your parts are coming in, if you're a commercial heat treater, it's washed off before you apply your polymer quench. If you're a captive, you want to make sure that whatever process was used before the polymer quench is washed off. You want to check quarterly for your biological growth. You can check contamination on site. It's very easy to do. Oils can be skimmed off with the application of a good oil skimmer. Periodic filtration and centrifuging will also work. Many induction hardening machines have an integral filter on them. So a centrifuge to remove tramp oil, this is what it looks like before and after. And when I say tramp oil is any oil that is not designed into the product. So in a polymer quench, any oil that leaks in is a tramp oil. So how do you mix up a polymer? Well, polymers are more dense. They're heavier than water. So you don't want to put the polymer in first and then put the water in on top of it, because then it requires a lot of shear and agitation to get that polymer to mix. Notice I use the word shear. You're going to have to shear that polymer, which we showed already is a bad thing because it changes the viscosity of the polymer and it changes the cooling properties. Now, when you dump and recharge a system, your supplier can offer you what's known as a machine cleaner. You can add a small amount of a machine cleaner to clean up any dirt and residue and still run your polymer quench. You should also completely change everything out, because then you have less risk due to biological contamination and oil contamination. We have here 3 different cooling curves for product A and polymer quench 1. You can see that with product A, not only does the cooling speed change from the red to this pink, but so does the vapor blanket stage. The difference between these two is the polymer viscosity itself. The shorter, less viscous polymer used in Polymer Quench 1 here provides more uniform cooling and more uniform vapor blanket lengths, which is shown here. So by controlling it between 12 to 15%, which is a very common concentration, market product A has a vapor stage all over the place. Whereas you can see the vapor blanket phase for Polymer Quench 1 is more tightly controlled. And the cooling performance will remain stable if you select the proper. Now here what we did is we heat treated the stainless steel round bar. And what we did is we used 50 milliliters of polymer and a diameter of, it was 50 millimeters in length and 50 millimeters in circumference. And we used two different polymer quenches. Again, the difference is in the viscosity. The shorter the polymer chain, the less viscous the polymer is, and you show less mechanical shear and thermal degradation by shortening the polymer chain length. And you can see here that after 6 months, the cooling curve is relatively the same for Polymer Quench 2 with the short polymer chain and less viscosity. Also, because the Polymer Quench 2, the cooling performance didn't change over that 6-month period, it didn't have to be dumped and recharged. Because it's less viscous, it goes back into solution much easier. It doesn't require the shear and agitation that a thicker, heavier, more viscous polymer will. Because it goes back into solution more easily, it doesn't plate out on the part, it doesn't plate out on the fixtures, it doesn't plate out on the machine, and it doesn't, more importantly, plate out on the parts and get dragged out and have to be replenished. So getting back to our 3 points that we asked at the beginning of the presentation, why do we need a polymer quench? Well, it's a safer, low-cost alternative to oils. A polymer quench can be used in its most common form as an induction hardening, but it can also be used in certain cases in through hardening and used in batch furnaces or continuous belt furnaces. What should we do for maintenance of a polymer quench? Well, you need to start with running daily concentration checks and providing regular samples to your supplier. Because remember, CQ9 states that if the bath or solution is older than 4 months, you need maximum cooling rates and you need cooling curves. Well, your supplier will also run other tests, such as the viscosity, to make sure that the polymer hasn't sheared. Refractive index, to once again make sure the polymer hasn't sheared. Your supplier will run biological tests if you've been having a history of bacteria and yeast, mold, and fungus. Your supplier will also run the cast iron chip corrosion test. All of these will set up a proper maintenance system and preventative maintenance, and the data will tell you when to dump your machine. Instead of, well, we always dump it every three months, or we always dump it once a month. Let your supplier use data to tell you when to dump the machine. Can we reduce the amount of maintenance for a polymer quench? Absolutely. Once again, start with your daily concentration checks. You may not have to add polymer every day, but you should be adding it 2 or 3 times a week. By adding polymer back into your tank, you're adding back corrosion inhibitor, you're adding back biocide, you're adding back the alkaline materials to make the pH where it needs to be. And also by selecting the proper polymer, one that doesn't have a thick viscosity, one that is thinner in viscosity. It's not going to play out on your machine. It's not going to play out on your fixtures. It's not going to drag out as much. So your maintenance, you're going to have a cleaner machine, and your maintenance of that cleaner machine is going to be much easier than that thick, viscous polymer. So I want to thank you for your attention today. And please, during the question and answer session for this paper, I will be available online. Once again, my name is Greg Steiger. Keisuke Kuroda was our co-author of this paper, and here's our contact information should you have any